All right, let's get this unit started. Now this unit is called the unit circle. And in this lesson, we're just going to introduce the idea of the unit circle. We're actually not going to do a whole lot with it, but we're going to pick it up again in the next lesson and expand on that. So what in the world is a unit circle? Well, you see here we've got two circles drawn, and these are x and y axes. So a generic regular circle, you could say, has a radius of r. The unit circle, the only difference is that it's got a radius of exactly 1. Instead of just having a radius of r, we've got a radius of 1. And what we're going to do with these circles a lot of the time is we're going to drop a perpendicular line to our x-axis. So we've got a point on our unit circle here. Let's call this is the generic point x, y. And we can get that on our unit circle as well. We've got the point x, y. That is anywhere on the circle. You could have the point x, y, depending on what x and y are, is determined by the circle itself. So from that point, x, y, we're going to drop a perpendicular line to the x-axis. So here's a right angle, and here inside my triangle, this is angle theta. That makes an angle with the x-axis. So looking at this triangle then, the length of this side on the bottom here, this is going to be length x. The height of my triangle here is going to be height y. And if I wanted to use this triangle to write my trig ratios, my sine, cosine, and tangent, I'd have something like sine theta equals, well, let's see, sine is so opposite over hypotenuse, so opposite y over hypotenuse r. I've got my cosine theta, which is, let's see, adjacent over hypotenuse, so adjacent x over hypotenuse r, so x over r. And I've got my tangent trig ratio, which is opposite over adjacent y over x. So in general, that's what we're going to be using today, is these trig ratios of x and y in a circle. We don't always draw the circle. Sometimes we just have the point, we drop a perpendicular, and we do our trig ratios from a triangle. So what makes our unit circle special? Well, we can do all those same steps on our unit circle. So drop a perpendicular. This is still length x. This is still height y. But when I start to write my trig ratios now, I've got, let's see, sine is opposite over hypotenuse. So you're going to put theta in here. Theta is always next to the x-axis. So theta is opposite over hypotenuse is y over 1. Well, that's just y. So in the unit circle, my y coordinate, this is going to be sine. And if I do cosine, so I've got cosine theta equals adjacent over hypotenuse is x over 1. Well, x over 1 is just x. So what I've got here is still then x over 1. And my x-coordinate then, cos theta equals x, is going to be cosine. So if I have my point xy on my unit circle, I can know right away what the cosine of the angle is. What the sine of the angle is just by looking at the point on the unit circle. Tangent is still, it's not going to simplify so nicely. It's still opposite over adjacent. It's still y over x. So that is still a fraction. It doesn't simplify out so nicely. So we're going to do a whole lot of work with the unit circle in the next couple lessons. But for now, just put the unit circle aside, and we're going to focus in on this kind of a circle that could have any radius going through a point x, y. So what we just did up there when we dropped that perpendicular line to the x-axis, that was called drawing your reference triangle. So a reference triangle is just from a point, this is a right triangle, triangle drawn to the x-axis. And again, it is very important that it is the x-axis. It's always going to be the x-axis, never the y-axis. So if I'm looking at this next example, they haven't drawn in the circle, but you could imagine a circle going through this point 3, 4. And from that point, again, we are going to drop a perpendicular line to my x-axis, always to the x-axis. There's a right angle. And that lets me make a triangle here that is with theta. Now notice that theta is not an angle drawn in standard position. It's always the angle drawn to the x-axis. So it's always going to be an acute angle, which is kind of nice. And from here we can do SOHCAHTOA. So we said in our previous example that the distance here along the x-axis, well, let's see, that's going to be my x-coordinate. So look in here, this is going to be a -3 here on this triangle. And the distance here, this is going to be my y-coordinate, is going to be 4. So this is one of the few times where on a triangle you're actually going to put a negative on the triangle itself. And that's just to say we're going in the negative x direction and then the positive y direction to get to my point on that circle that I could see. Now to find sine theta, I'm going to need the hypotenuse of my triangle, so I can use a squared plus b squared equals c squared if you like. So that would be then negative 3 squared plus 4 squared equals c squared. That would be 9 plus 16 equals c squared, or 25 equals c squared, and square root of that 5 equals c. My hypotenuse is always going to be positive, so even though I could, when I take the square root, say this is plus or minus 5, when I'm finding a hypotenuse, it's always going to be positive. The other sides are going to depend on what quadrant you're in, whether they're going to be positive or negative. So hypotenuse 5. Now, some of you may recognize this, 3, 4, 5, as what we call a Pythagorean triple, which means it's the Pythagorean theorem with all whole numbers. And these show up quite a bit. So the 3, 4, 5 triangle is fairly common. You'll see that one quite a bit. You might also see the 5, 12, 13 triangle, or the 8, 15, 17 triangle. If you want to memorize these, they might save you a bit of time in the future, but if you don't, you can always find them again using the Pythagorean theorem. That is not a problem at all. All right, so once we've got our hypotenuse going on here, then we can find sine of theta using SOHCAHTOA. So from this theta, opposite 4, hypotenuse 5, we're looking at 4 over 5. And in this case, we're always going to be looking for an exact answer. We're going to use fractions, we're going to use roots, we are not going to use decimals. So get used to that, where we're having a fraction answer and sometimes even a square root as part of that fraction answer. All right, let's take a look at another example. What if I have a circle going through the point, let's call this point t minus 3 minus 6. I have a point and I want to find cosine theta of the reference triangle going through that point. So in other words, we need to actually draw this picture. We don't need all of these pieces. Actually, what we really need is the point on the reference triangle. So let's see if we can do that. So the point negative 3, negative 6, so let's see, that would be negative 1, 2, 3, negative 1, 2, 3, 4, 5, 6. You don't have to be super exact at this, but you do need to figure out what quadrant that you're in, and then draw the line going to it. From there, to draw a reference triangle, again, we're going to drop a perpendicular line from that point to the x-axis. Didn't draw these very exact. This should actually go through here. This is supposed to be a right angle. Sorry about that. And let's label my point. This is actually, so this is negative 3, negative 6, which means on my triangle, the x here, this is going to be negative 3, and the y here is negative 6. Now again, to find the cosine, we're looking at SOHCAHTOA with a hypotenuse in it. So I'm going to need to use a squared plus b squared equals c squared to find my hypotenuse. So let's see, if I do negative 3 squared plus negative 6 squared equals c squared, 9 plus 36 equals c squared, and then 45 equals c squared, and c equals root 45. Now, is that actually simplified root 45? No, it's not. I can simplify this by looking for, again, perfect square factors. So 45 is 9 times 5, and 9 is a perfect square, so I can rewrite this as root 9 times the root 5, and I know that root 9 is just 3, so this is going to be 3 root 5. Do you need to simplify? Yes, you do. So watch out for those that are not simplified. Okay, so then I want to find the cosine, so let's put this on here. Actually, this is going to be then 3 root 5. Remember, hypotenuse is always positive, so even though these other two are negative, not a problem. Hypotenuse is going to be positive. So I'm thinking cosine is adjacent over hypotenuse, so adjacent, here's my angle theta, sorry, theta is always with the x-axis, so adjacent to theta, negative 3, hypotenuse, root 3 over 5, so this is negative 3 over 3 root 5. I can simplify this again. I don't like having a root in the denominator, so this is going to be, in order to simplify, I'm going to multiply top and bottom by that root, just the root, so root 5 over root 5, because root 5 times root 5 is going to be 5, so on the top, this gets me in negative 3 root 5 over, or root 5 root times root 5 is 5, times 3 is 15. Am I simplified at this point? Not quite. I can simplify between the numbers outside the square root, so don't try to cancel the root 5 and the 15. Even though they have a common factor of 5, the root 5 is protected by the root. But I can cancel the numbers in front, so 3 and 15 share a common factor of 3. So delete, divide by 3 gives me a 1 here, divide by 3 gives me a 5 down here, and this would be, as a finally simplified answer, negative root 5 over 5. 5. Beautiful, simplified, final answer. There you have it. So again, reference triangle drawn to the x-axis, theta always with the x-axis. You might need to find your hypotenuse. Sometimes you'll have to find other things, as we're going to see in the next example, but we usually have to find a missing side using Pythagorean theorem or your memorized Pythagorean triples, and then you can find your trig ratio. So let's take a look at another way they could give you the same type of question. So now they're saying, given that theta is in quadrant 4, and they're giving you the sine ratio, and they want you to find the cosine ratio. So let's draw ourselves a little picture. Here's my x and y axis. I know theta is in quadrant 4 down here. This is where I'm aiming. And just kind of to start out with, I'm just going to sketch that in there. It doesn't really matter if you're super exact with this. It can be really rough. Here's my triangle. I don't actually know if this is smaller than 45. I drew it that small, no worries. Draw your perpendicular to the x-axis, draw in your theta, and then think about your trig ratio to figure out how to put these numbers on your triangle. So if sine theta is -3/5, remember that this is opposite over hypotenuse, so I'm going to put that on here. From theta, opposite is 3, hypotenuse is 5. And how do I know where this negative is going to go? Well, looking at this triangle, this would be a positive x, but a negative y, and my hypotenuse is also always positive. So let me just move this over a little bit so I can add in here. This is actually going to be then -3 on the y. Then I need to find cosine theta, and cosine theta is going to require this adjacent side, which I don't have at the moment. So you can either do Pythagorean theorem, 3 squared plus b squared equals 5 squared, and solve for b, or you can go, this is a 3, 4, 5 triangle, so this side must be 4. And because it's on the positive x direction, it's a +4 when I put it on my triangle. Okay, find a cosine theta then. I'm going to put cosine theta equals adjacent over hypotenuse, 4/5, and I'm done. That's it, all done. So again, that's another way that they can show you the same kind of a question, ask you to draw or make the trig ratio. Notice that in all of these examples, we never found theta itself. We actually don't even care what theta might be. We're interested in only the trig ratios. Now, up till now, we focused on what we've called the primary trig ratios, or the 3 main trig ratios that you see all the time. On the top of the next page, we're actually going to talk about some new trig functions. These are called your reciprocal trig functions. So, review again, SOHCAHTOA, sine, we know is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. These are all the ones that you know already. But now we've got these 3 new ones that we're calling reciprocal trig functions. Remember that reciprocal, what that actually just means is flip the function over. Or if you had a fraction 3/4, to flip that over, to take the reciprocal, we raise it to the power of -1, flip it over equals 4/3. If I have a whole number, something like 2, reciprocal is flip it over 1/2. So the way we've got these lined up right now, sine is reciprocal. Its reciprocal is this CSC, which is actually, if I spell it out, CSC stands for cosecant. CSC, whoops, I can't spell. CSC is actually read out cosecant. And what that means, it is the reciprocal function of sine. So this is 1/sine of whatever you've got. Cosecant, 1/sine. Or, in other words, flip over your trig ratio. So if sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. Okay, so reciprocal, flip over the fraction, flip over the whole thing, or flip over just the ratio itself, either way that you want to think about that. Secant, SEC, stands for secant, and it is flip over your cosine. So 1/cosine, or flip over the fraction hypotenuse over adjacent. And then the last one, cot or COT stands for cotangent. And that is, you guessed it, 1 over tangent. Flip over your tangent fraction. So this is adjacent over opposite instead of opposite over adjacent. So hopefully it's pretty easy to remember. Tangent and cot go together. Tan and cot, they're the only ones with t's involved. So they are flipped of each other. If you get confused with sine and cosine, cosecant and secant, the way that I remember these and which one goes with which is an S always has to go with a C. So sine starts with an S, its reciprocal is the cosecant. Cosine starts with a C, so its reciprocal must be secant. So one C, one S in each case. And again, in this lesson, we're not going to deal so much with flipping over the whole thing, although you could. We are actually going to deal more with flipping over the fraction, as you're going to see in the next example. So, given this triangle, which is your Pythagorean triple 5, 12, 13, we want to find the sine, cosine, tangent, cosecant, secant, and cotangent of each of these. So sine, cosine, tangent, this is something that you've been doing forever. So katoa, so sine is opposite over hypotenuse, 5 over 13. Cosine, adjacent over hypotenuse, 12 over 13. And tangent is opposite over adjacent, 5 over 12. So to find each of these, I could go back to their definitions, or I could just say, oh, I've already found sine, 5 over 13. Sine and cosecant are flipped, so this one must be 13 over 5. Again, that's hypotenuse over opposite. Cosine is 12 over 13, so secant must be 13 over 12, or hypotenuse over adjacent. And cotangent, well, tangent is 5 over 12, so cotangent must be 12 over 5, which is adjacent over opposite. So if you want to, you can find these directly, and maybe sometimes questions will ask you to find them directly. I find it easier actually just to find sine, cosine, tangent first and flip them over after that. Depends on you, what you're more comfortable with. Okay, so again, another way that you can see a similar type of question. Given that we're between pi over 2 and pi, we are told that the sine of our angle is 8 over 17, and we want to find all 6 trig functions. So again, we're going to have to draw ourselves a little picture to figure out what in the world we're talking about. So here I have my 4 quadrants. This is 0, this is pi over 2, this is pi, and this is 3 pi over 2. So if I'm between pi over 2 and pi, that must mean I'm in quadrant 2 over here. And again, just rough in, doesn't really matter if you're that exact, put in your angle and then drop the perpendicular. Sine theta is 8 over 17, so again thinking SOHCAHTOA, this is opposite over hypotenuse. So if I want to label these sides, oh yeah, here's theta next to my x-axis. Remember, theta always next to your x-axis. So opposite, here's my 8, and hypotenuse 17. Positive 8 because we're going in the positive direction, and positive 17 because the hypotenuse is always positive. And then we want to find all 6 trig functions. Well, in order to do that, we're going to need to find this missing side. So again, with our Pythagorean theorem, we can go, I might call this, well, this is x. So it's x squared plus 8 squared equals 17 squared. And solve that on your calculator. So this is actually then going to be 17 minus 8 squared and square root of that. And maybe you had this one memorized, that just gives you x equals 15. So if I put that, let's erase this for a second, if I put that on my graph, this is 15, but it's also in the negative x direction, so it's actually going to be a negative 15 because we're on the negative x-axis. This would be the point then, negative 15, 8. So watch out for those positives and negatives. Although the Pythagorean theorem is, again, this could be plus or minus, you need to think about what quadrant you're in, what axis you're on, in order to figure out if we're looking at a plus or a minus. If you had the Pythagorean theorem triple memorized, 8, 15, 17, you don't need to do the Pythagorean theorem. You can just write it down directly. That's fine. Okay, so we need to find all 6 trig functions. So we're given the sine already, so sine theta is 8 over 17. Please do write the theta in. Don't just write sine as 8 over 17. It just looks weird if you skip the theta, and I will take off marks, so be careful with that. Then I have the cosine theta is adjacent over hypotenuse is negative 15 over 17. And then tangent theta is opposite over adjacent is 8 over negative 15. To find now cosecant, so sine and cosecant are related, so cosecant then is going to be 17 over 8. Cosine and secant are related, so flip that over, 17 over minus 15. You can put the negative out front if you like, you can put it on top, doesn't matter, it can go on the bottom, wherever you want to put it. And then cotangent, again, flip over your tangent, so negative 15 over 8, and you're done. So again, all 6 means you do need to rewrite the original one, even though they give that to me right off the bat. I need to have all 6 written together. There's my answer. All right, last thing before we finish off with this lesson, what things are positive and negative in each quadrant? So remember that you have quadrants. These are quadrants 1, 2, 3, and 4. And maybe you remember from at the very beginning of the lesson when we were talking about the unit circle, we actually said something like, let me write it down here in the margin again. Cos theta is x and sine theta is equal to y on the unit circle. We had x over r and y over r. But that means if I have a point on this circle, in this first quadrant, my x value is going to be positive, my y value is also going to be positive. That means my cosine is going to be positive in this quadrant, and my sine is also going to be positive in this quadrant because a point on the circle has a positive x, positive y. However, if I draw a point over on this side, this is going to have a negative x value and a positive y value. Since cosine is my x value, cosine is going to be negative and sine is going to be positive. Now, if we're not dealing with the unit circle, they don't work out to be those exact values, but the signs still match. So even though it might have a radius here, so I can't just take the x value directly, that's why I ended up with these fraction values, the sine of the x value is going to match the sine of cosine. So again, down here, if I have a point, I have a negative x, negative y, so that is going to be a negative cosine and a negative sine. And last but not least, over here, I've got a positive x, negative y, so again, positive cosine, negative sine. So let's take a look at what our actual questions are. What quadrants can theta lie in if sine theta is greater than 0? That means sine theta is, if it's greater than 0, sine theta is positive. And cosine theta is less than 0, or cosine theta is negative. So I need sine theta to be positive. Well, what quadrants does that happen in? I've got a positive sign here, positive sign here. The other two signs are negative, so sine theta is positive in quadrant 1 and quadrant 2. And cosine theta is negative, well, not quadrant 1. Quadrant 2, yes. Quadrant 3, yes. Not quadrant 4. So this happens in quadrant 2 and quadrant 3. So we get both things happening, which is the and part, only in quadrant 2. That would be my final answer. So cosine negative, sine positive only happens in quadrant 2. Now let's see. Part B asks where sine and tangent have the same sign. So we know the sign of sine in each of these quadrants. We need to figure out what the sign of tangent is. So if you remember, we wrote up there that tangent theta was y over x. And so in order for tangent to be positive, I would need to have either 2 positives or 2 negatives, because a negative divided by a negative is also positive. For tangent to be negative, I would have to have 1 negative, 1 positive, because a positive and a negative dividing will give you a negative. So 2 positives, this means this is going to be tan positive in this quadrant. A positive and a negative, that's going to be tan negative in this quadrant. This one, 2 negatives, well, that's going to be, again, tan positive. And a positive and a negative, that's going to be tan negative. So I need to know, where do sine and tan have the same signs? So let's think about that. That's going to be, okay, here sine is positive, tan is positive, so that is quadrant 1, because they're both the same sign. Here I have positive and negative, so not the same sign. Here I have sine negative, tan positive, not the same sign. And here I have negative, negative, again, we've got the same sign, that's quadrant 4. All right, one more example, last one. asks us where cotangent and secant have opposite signs. So the reciprocal functions will always have the same signs as their original function. So cotangent will have the same sign as tangent. And secant, remember S and C, so this starts with an S. This has to be the reciprocal of cosine because it has a C. So we want to know actually where tangent and cosine have opposite signs, one positive, one negative. So looking in my first quadrant, tangent and therefore cotangent is positive, cosine and therefore secant is positive, so they have the same sign, so not the quadrant we're looking for. In quadrant 2, tangent is negative, so cotangent is negative, and cosine is negative, so secant is negative. Again, they have the same signs, we don't want that, we want them to have opposite signs. Quadrant 3, tangent is positive, so cotangent must be positive, cosine is negative, so secant must be negative. There we have opposite signs we're looking at, quadrant number 3. And then last but not least, double check, tangent is negative, so cotangent is going to be negative, cosine is positive, so secant is going to be positive. Again, we've got opposite signs, so we're looking at quadrant 3 and quadrant 4. Now, one little mnemonic that I like to help me to remember which quadrants have positives and negatives, and this is only for the primary trig ratios. From there, you still have to relate them to their reciprocals. We have something like, all students take calculus. In other words, in the first quadrant, all my trig ratios are going to be positive. Okay, cosine's positive, sine's positive, tangent is positive, all the reciprocals are going to be positive, everything is going to be positive, all positive in the first quadrant. In the second quadrant, only sine is positive. So sine is positive, and everything else is going to be negative, except of course the reciprocal of sine also matches the sign of sine. So cosine negative, tangent negative, only sine is positive. T stands for tangent, so tangent in this quadrant is positive, but cosine and sine are negative. And C stands for cosine. Only cosine is positive in this quadrant, tangent and sine are negative. So if you remember that, all students take calculus, or all students take chemistry, whatever you like, make up your own that you can remember better. A, S, T, C, 1, 2, 3, 4. That'll help you remember what's positive in each quadrant. All right, so that's it for this lesson on reference triangles. Good luck on your homework and your mastery check.